Per Bloomberg in 2024, lithium-ion battery pack prices fell 20% to about $115 per kilowatt hour. It's the biggest price cut since 2017. At these prices, it's cheaper to buy Chinese, even with tariffs of 25%, 35%, and perhaps 120%. Central to this trend are the price and technology developments going on in a specific type of battery, lithium-ion iron phosphate, or LFP. LFP batteries were once seen as cheap and low-end, suffering fundamental chemistry weaknesses. Leave it to China to engineer their way around such limits. In this video, one of the most revolutionary cost curves in energy history, China and the LFP. Lithium-ion batteries have two electrodes, the cathode and anode. The anode is usually just graphite, so the cathode is the battery's most expensive part, over 70% of its value, and how we distinguish between them. In the industry, there are three major chemistries. First, there are the two ternary batteries. They're called that because their cathodes mix three materials in varying ratios: nickel manganese cobalt, or NMC, and nickel cobalt aluminum, or NCA. The ternary batteries boast higher energy densities, meaning that they can store more energy in the same size and weight, so you can make a lighter battery pack, letting EVs potentially go further on a single charge. This is great, but it comes at a cost. Nickel and cobalt are rarer, more expensive materials, which is a big deal since raw materials, again, are 70% of a battery's cost. And the ternary batteries' higher energy densities raise thermal risks, potentially leading to something called thermal runaway, meaning a fire. The LFPs are the third major chemistry, using a dual chemistry cathode made from iron phosphate. There's no cobalt or nickel. Since iron and phosphorus are far more common materials, LFPs hold a substantial cost advantage. They can also better hold their initial energy capacity after many charge and discharge cycles. The problem is that LFPs suffer lower energy densities, about 90 to 160 watt-hours per kilogram. NCA, on the other hand, ranges 230 to 260 watt-hours per kilogram, and MMC the highest at 250 to 320 watt-hours per kilogram. This gap does narrow at a practical level, but it's nevertheless substantial. So, all things being equal, EVs powered by LFP batteries will not have ranges as long. That sucks, but an upside is that the lower energy density also lowers the risks of thermal runaway. So to make a big generalization, batteries have three angles: performance, cost, and safety. LFPs have cost and safety, but not performance, and MC and NCA have performance, but not cost and safety. You can't have everything. In the early years of lithium-ion, the first batteries were lithium cobalt oxide, or LCOs, an older chemistry that used about 0.95 kilograms of cobalt for each kilogram hour of energy capacity. As lithium-ion got more popular, though, it became clear that using this much cobalt, which had to come from the Democratic Republic of Congo, was not economically, morally, or environmentally sustainable. This is how ternary battery chemistries like NCA, MMC, and a third one I haven't mentioned before called lithium manganese oxide, or LMO, first gained traction. They still used cobalt, but far less of it, 0.14 kilograms in the case of NCA and 0.4 kilograms for NMC. In the 2010s, pioneering EV cars in the West, like the Chevrolet Volt, the Nissan Leaf, and the Model S, the Tesla Model S, ran on battery packs made with ternary cathode chemistries. Meanwhile, in China, China's first EV makers adopted LFPs for their new energy vehicles, particularly buses, due to the influence of early government industrial policies like the thousands of vehicles, tens of cities policy, or TVTC. Launched in 2009, TVTC issued subsidies to various municipal governments to have them purchase public service fleets like buses, taxis, and government cars. The idea was to address urban air pollution, energy security issues, and make Chinese EVs great. Chinese companies like BYD adopted LFPs early on due to cost and safety concerns, becoming strong pioneers in the space. And for the first few years, LFP chemistries dominated the Chinese EV industry. In late 2016, however, the Chinese government started changing its subsidy policies in an attempt to push the EV industry to produce cars more attractive to consumers. The policy linked car subsidies to several factors like higher energy density, longer driving ranges, faster charging rates, and fuel savings. If the EV had range of less than 150 kilometers, then no soup for you. This favored cars with ternary battery chemistries, which could unlock the juiciest subsidies, offer the lowest prices, and capture market share. And over the next 3 years, even longtime LFP loyalists adopted ternary, like BYD in their 2017 models of the Tang 100, Song EV300, and the Qin EV300. By mid-2019, ternary batteries reached about 70% share of installed capacity. The market share of LFPs, on the other hand, fell to 30%, and in some quarters, even lower. Two major developments reversed this trend and revitalized the LFP. The first started in June 2019, when the Chinese government signaled that the EV cash subsidy policies instituted 3 years earlier would be gradually withdrawn. Now, people have known this was coming. The scale of the subsidies had gotten to be somewhat significant. There were also unsavory reports of subsidy cheating, with companies making up fake customers or registering fake cars for free money. The Chinese government probably felt it was time to move on to non-monetary forms of support, like streamlining the issue of driver's licenses to those with EVs. However, the size and schedule of the withdrawn subsidies somewhat surprised the Chinese EV industry. Right off the bat in mid-2019, the subsidy was reduced by 50%. More chunks of the subsidy would be removed in each subsequent year. This aggressive sunsetting leveled the cost playing field. EV makers rushed to switch back to LFP, and at the same time, LFP makers rolled out new technologies to curb fundamental weaknesses. Back in 2021, many years ago, I did a video about CATL, the Chinese battery giant. And in that video, I briefly mentioned the BYD Blade battery, though didn't say much about it. I probably should have, since as it turns out, the BYD Blade remade EV battery manufacturing. BYD first introduced the Blade in March 2020, and it debuted in the company's BYD flagship sedan, the Han, a few months later. So what's the big deal about the Blade? An EV battery has 3 manufacturing levels: packs, modules, and cells. Cells are the battery's smallest and most fundamental blocks. They have the cathode, anode, and electrolyte chemicals in various shape factors like pouches or cylinders. There might be thousands or even tens of thousands of cells in a pack. Sliding so many cells into a pack directly presents challenges. Handling so many at once is hard, and there are concerns about maintaining the pack's structural integrity. So what traditional EV battery manufacturers did was to group battery cells into modules. The number of cells in a module is arbitrary, ranging from 4 to 12, but it offers an intermediate building block towards the final pack. What BYD did with the Blade was to entirely skip the module, sliding cells directly into the battery pack, ergo the name cell-to-pack or CTP. The idea is to compensate for LFP's fundamentally worse energy density by making maximum use of the pack's volume. To maintain the whole pack's structural integrity, BYD uses a cell form factor called the prismatic cell. A prismatic cell is a long and flat pouch of many stacked layers of materials inside a rigid rectangular metal casing that offers structural integrity. To help prevent swelling, there might be a clamp. BYD re-engineered the prismatic cell form factor into a very long, ultra-thin shape. The metal casing basically spans the width of the whole battery pack, ergo the name Blade. The Blade was a game changer. The extended range version of the 2020 Han EV had range of 605 kilometers. Note that this and other numbers cited here were calculated using a rather forgiving range formula out of Europe called NEDC, so I can't say they are comparable with US range metrics. Anyway, 605 kilometers was in the same neighborhood of the Model 3, with 668 kilometers, and the Xpeng P7 with 706 kilometers. But those EVs were premium EVs running ternary batteries, costing anywhere from 270,000 to 330,000 RMB. The Han, on the other hand, got its range numbers using just LFP batteries and cost just 210,000 to 258,000 RMB. CTP gives LFP battery packs about 85% the energy density of a conventional NMC battery. And those ternary batteries have a tough time adopting CTP for themselves due to their hotter temperatures. Soon afterwards, other major Chinese EV battery makers adopted the concept. CATL, for instance, brought up their very creatively named CTP technology, which they use for their Qilin battery pack. LFP battery volumes overtook NMC in 2021, and by 2023 they accounted for nearly 70% of EV installations per the China Automotive Battery Industry Innovation Alliance. That's a mouthful. NMC batteries are still better in energy density, but are now primarily used for the premium high-performance cars, for example the Xiaomi SU7's Max and Ultra versions. Another major helpful development for China involved patents. The current lithium-ion battery structure, with its focus on cathodes, was discovered and patented by the American scientist and Nobel winner Dr. John Goodenough. He also pioneered the LFP cathode too. However, the LFP as invented by Goodenough was not commercially performant. In particular, there were poor electrical conductivity issues. The charge carriers could not move between the cathode and anode fast enough during charge and discharge. Years later, key innovations in carbon coating and process technologies were invented, making the LFP a commercially competitive product. These were patented by researchers at universities and public entities in Canada and Europe. All these patents were then consolidated into a single Swiss entity managing global licensing. According to the IEA, there was a deal made in the 2000s or 2010s that allowed the Chinese battery makers to use these LFP battery patents for free, but only for their local markets. Everyone else had to negotiate for and pay a license fee. This strange sort of patent shield allowed the Chinese to lean into and build up proficiency in LFP. Meanwhile, the rest of the world's EV battery makers pursued non-LFP structures, hesitating at the patent licensing issue. These patents finally expired in 2022. On one hand, this meant that foreign battery makers can finally access and use the LFP chemistry themselves without worrying about these licensing fees. But anyone trying to do that was starting out massively behind, because in the years leading up to 2022, the Chinese battery makers had built up immense LFP supply chain proficiency. They had the cell-to-pack innovations, massive economies of scale, material sourcing, talent pipelines, and more. Until 2021, BYD practiced vertical integration. BYD batteries were only for BYD cars. This was necessary in the early days when the technology was immature, but it also allowed other third-party makers like CATL and LG Energy Solution a spot in the market. In 2021, however, this changed and BYD started selling its Blade batteries to third parties like Toyota, Ford, and other car companies. This introduced a major new Tier 1 battery supplier to the market, triggering a price war. This is on top of the already insanely competitive situation in the Chinese EV market. The Financial Times recently reported that a new Chinese EV model hits the market every 2 days. Car makers are looking for ways to differentiate themselves, particularly at the high end. More range, faster charging, you know what I mean. So LFP makers are looking to new production methods or recipes to fulfill those needs. An interesting one is LMFP, lithium manganese iron phosphate, where you add manganese and get a battery with higher energy density than your ordinary LFP. Another is the double firing process flow. Traditional LFP makers take the raw precursors of their cathodes, lithium salt, iron phosphate, carbon, and then they fire those ingredients in a single high-temperature run to trigger certain chemical reactions and sinter particles. The issue with single firing, however, is that it can cause uneven grain growth and poor carbon coatings, leading to inferior conductivity issues. So the new idea from the Chinese is to dual fire. You first partially fire up the precursors at a lower temperature, then you mill and carbon coat the resulting particles before doing a second firing. You get more uniform and similarly sized particles, translating to better, more consistent performance. Perfect for long-range, fast-charging EVs. A significant factor in the lithium-ion battery price crash was a concurrent crash in raw materials prices after 2022. As I mentioned earlier, 70 to 80% of the cost of a battery cell is the cost of its materials. And in the case of LFP, 80% of that material cost is the cost of the iron phosphate and lithium alone. In 2023, new lithium sources came online in Australia, Chile, and Argentina. This rapidly reversed what had been a lithium shortage in 2022, causing prices to crash. The glut has caused a few mines to produce losses, but their Chinese operators are injecting cash to keep them open and mining for political and technical reasons. And as for iron ore, iron prices reversed from its 2022 highs thanks to China's real estate crisis. That crisis has mothballed China's crude steel production, which in turn caused iron ore prices to fall 15% in 2024 alone. All this means that Chinese EV battery makers can cut battery prices, and they have to due to the intense competitive environment, and still make profit. In 2024, CATL revenues declined 9%, from 400 billion RMB to 362 billion RMB, but gross profit margins rose 19.2% to 24.4%. Now, I do admit that 24% isn't exactly super exciting. It's nothing like Meta's 81% margins or even Apple's 42.7% gross margins, but at scale, those add up. The LFP batteries' crashing prices has had spillover effects in other industries beyond EVs. I've recently been researching a few videos relating to utility-scale stationary energy storage systems, ways to store power produced by wind or solar during times of low energy demand. You lose some amount of energy from converting the power into something else and then getting it back again, but the idea is that it is cheaper than trying to ramp up a coal plant or something else like that during peak hours. It's arbitrage. The canonical system is pumped storage, which I covered in an earlier video. It's very simple, a reservoir up on a hill. When power is cheap, we pump water up into it. When we need power, we drop water down. But there are other methods that are a bit stranger. For example, my personal favorite is power to gas. This is where we use a method called electrolysis to split water molecules into hydrogen. And then in a second step, we capture carbon dioxide from the air and fuse it into the hydrogen to produce methane. Or in other words, natural gas. The idea being that we can plug into existing LNG infrastructure. This particular scheme and virtually all others are now uncompetitive, as the crashing costs of LFP batteries have tipped the market to BESS, or battery energy storage systems. LFPs were already favored for BESS prior to 2021 due to their cheaper material costs and resistance to thermal runaway. But the Chinese EV boom in 2021 has really set BESS on fire, figuratively. They're not competitive in sheer capacity size yet. They only provide 1 to 2 hours of power rather than the 4 to 12 hours that pump storage can. But BESS are cheap, incredibly cheap, and are simple to build. The whole system is put inside a standard-sized container and brought over to the site, and we just leave them there. And while there are legitimate fire concerns with BESS, vendors are getting better at controlling them. Billions of dollars are pouring into BESS projects across the United States, particularly in the states of California and Texas. $11.45 billion in the first half of 2024 alone, with funds coming not only from government, but also banks and infrastructure hedge funds. How those projects will be affected by tariffs, though, we've yet to see. The Chinese EV and stationary battery industries continue to churn forward. Market analysts point out that LFP prices will continue to fall, but probably nowhere near as fast as they were in prior years. I think one of the most interesting industry developments to keep an eye on, though, is the forthcoming technology progress of sodium ion. I covered this briefly in another video a few years back and have not mentioned much about it since, but CATL, BYD, and Huawei are all pursuing it. Sodium ion suffers fundamental energy density shortcomings against lithium ion, but sodium is far more accessible than lithium, seems to be able to charge faster, and energy density numbers are getting better. Considering how optimized the LFP supply chain is, I wonder if sodium will be as impactful. We'll have to wait for the product, but we shall see. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.